we're here at the Oregon State University's WESRF laboratory with Annette Von Juan, and she's a professor here dealing with the wave energy program. Thank you for having us here.
Thank you for coming.
And tell us a little bit about this fabulous facility here.
We're here in the Wallace Energy Systems and Renewables facility. It's the highest powered energy systems lab in any university in the nation. And I'm going to take you down where we're going to show you our wave energy linear test bed.
Awesome, let's go take a look at it.
We have a dedicated feeder from Pacific Power, and our input supply is 750 kVA.
Wow.
So that allows us to test a wide range of power levels for a variety of energy systems work.
Equipment here, what do you call this thing? What does it do?
This is our wave energy linear test bed, and it's designed to create the relative motion between a heaving float and a central spar. This central spar is relatively stationary at the sea surface, whereas the magnet assembly is attached to a heaving float. So as that float heaves up and down, this magnet assembly creates a changing magnetic field surrounding the spar that contains the armature. So this buoy on the wave energy linear test bed is our 11th prototype. And over the past 10 years, we've been developing what we call direct drive technologies, where we have a direct coupling of the buoy's velocity and force to the generator without using hydraulics and pneumatics. And we've been advancing these technologies with a strong collaboration with our partner industry, Columbia Power Technologies. And I'd like to introduce you to those engineers. We have Al Schecker, Ken Reinfrank, and Joe Pradell. And we're going to run up this linear test bed. Are you guys ready? We are. All right, excellent. So now we're controlling the linear test bed with actual wave data. And we have two wave monitoring devices. One that sits on the sea floor, it's called an AWAC, acoustic wave and current. And using a gimbal and an acoustic eye, we're able to measure the wave magnitude, period, and current. We have another wave rider device that sits on the sea surface that also measures wave magnitude and period. And we're able to correlate that data along with our buoy performance when that buoy is out in the ocean. We place those devices such that they're on the same wave set so that then we can bring that back into the lab and actually program the linear test bed with the same ocean climate that that buoy was experiencing. Here is a pop-up buoy that allows us to remotely pop up a float system so that we'll always be able to retrieve this system even if the surface expression is compromised. This is the ballast tank. This attaches to the bottom of the spar, and it was designed in a modular way so that it could be removed for linear testbed testing. And what this does is it gives us ballast control to control the stability of the buoy. When this buoy was deployed and we had our wave monitoring device, it was experiencing an average summer climate. And off the Oregon coast, the summer wave energy potentials they average about 1.5 meters. But over the winter, we average about 3.5 meters. So yes, when we capture data and test in the ocean, in the summer, we're experiencing a much milder ocean climate.
I understand this is a prototype, so really explain how large this thing is going to be.
This is a 10 kilowatt prototype, and the size difference, this full buoy out in the ocean is a little over 20 feet tall with a float that's about 11 feet in diameter. A 100 kilowatt device would be about 80 feet tall and 30 feet in diameter.
So you don't need deep water to put this into. You can run this, you guys are going to just be off a mile or so off the coast, right?
Well, about 2 to 3 miles off the coast. A pretty optimum depth is 150 feet. That's before the waves start to break.
So it's about to break.
Right, we want the waves before they start to break, before they start to lose their energy. We really want those heaving swells. And we want to also optimize the cost of the mooring system, the power takeoff cable. And that's why 150 feet is a pretty optimum depth. These devices are going to be designed for about a 20-year lifespan. We've built the generator here in our lab, and then the fiberglassing has been done at Plastifab.
So this is really a homegrown project in all
Absolutely. It's a tremendous collaboration of students, industries like Columbia Power Technologies, utilities, as well as manufacturing with companies like Plastifab. We've learned a tremendous amount through this year of research and testing. This has been a year contract with the Navy, Columbia Power Technologies, and OSU working together, where we evaluated 18 different direct drive technologies. We down selected to 5, built all 5 at the 200 watt peak level, tested them on the linear test bed, simulated them, even drove those simulations up to 100 kilowatts so that we could get full 100 kilowatt designs and cost of energies. That led into the development of this 11th prototype, this buoy, and we've learned a tremendous amount with Columbia Power Technologies on the bearing surfaces, on the mooring system, on the whole deployment dynamics, and now we're bringing it back into the lab to further test, do force control, as well as test the bearing systems again on the linear test bed, friction coefficients, so that we can optimize and help Columbia Power Technologies really move the advanced topologies to commercialization. We need to learn a lot about the sliding surfaces, these bearing surfaces, the mooring system, the deployment process, and so that's what we were learning for really how best to move that optimum topology toward commercialization. So there are several different mooring options. There's a tension moored system, a top moored system, there's a semi-taut, a catenary system, and a heave plate. This recent testing we did with a heave plate. So we had a 3,000-pound heave plate that hung 15 meters below the surface, connected to the bottom of the spar. And what that did is that dampened the response of the spar so that we had good relative motion between that heaving float and that central spar. It showed that it worked very well, and it will be part of our process of designing that mooring system, and we're using some fantastic tools like OrcaFlex in order to optimize that.
And do you have one of those in the facility here?
We do. We use OrcaFlex simulation software here in our facility.
And do you have one of the mooring pieces here?
We actually have our float and heave plate on display right now at the Hatfield Marine Science Center.
Oh, wow. Oh, no, that's great. I've been to that place. It's wonderful. It's great. Nanette, thank you so much for being here, and we look forward to seeing you again.
Absolutely. Thanks for coming.
And I'm Gordon Westphal, bringing you the tools to be sustainable today.